Okay, this is the second example of solving complex equations. I'm using the same template as I did for the previous example. So in this case, we're going to just be mindful of the definitions that we have there. And again, cos x equals e to the ix plus e to the power of minus I, e to the iz plus e to the minus iz all over 2. That's cos of z. An equivalent expression there for sine of z. We have the hyperbolic functions down there as well, cosh and sine. The last one here is log of x, and in the form log where z equals log of z, where where that is in the form log of x plus iy. We can re-express that as where log of x is a complex number. We can re-express that as the natural log of x squared plus y squared. That's the natural log of the modulus plus I times the argument of z. So this is the modulus here, or the log of the modulus, even more to the point. That's the modulus there, and that's the argument theta. Okay. Now, in these sort of examples that you can there is a sort of a simplification that you can use, or it's a very obvious answer. You might sort of see pi over 2 spring out of nowhere if you're looking at some textbooks, and you just sort of say, where did that come from? So just suppose we have z equals a plus ib. Okay. Now, if the imaginary term was if we only had the imaginary term and the real term was 0, for example, 0 plus ib, that just imaginary only. Well, therefore, the argument of z would necessarily be pi over 2 if a is 0. If you just look at the Argand diagram there, the imaginary part there, a is 0 and b is up here somewhere. So the argument there is theta is pi over 2 by definition. So it's just like, it's just sort of a, how should I say, you can sort of rely on that. Now, just as a remark, it sort of helps to justify it in your exam paper if you're doing a question like this. So solve the following complex equation: cos of x equals 7. So what we're going to say is cos of x equals cos of z even, sorry, I keep saying x, cos of z equals iz plus e to the minus iz over 2, and let that equal a 7. Okay, so let's simplify that out. E to the iz plus e to the minus iz, and let that equal 14. Multiply above and below by 2. Now what we're going to do here is let w equals e to the iz. Necessarily e to the minus iz is going to be 1 over w. Okay. So we can rewrite that expression here, this expression here, as w plus 1 over w equals 14. Okay. So we got a quadratic expression in w. So I've just gone a bit too far there. So w plus 1 over w plus equals 14. This expression here, let's just multiply each term by w. So we have w squared plus 1 equals 14w. Or let's just rearrange that as w squared minus 14w plus 1 equals 0. So this is something we can use. This is a quadratic. What we can do there is find the roots of that. And what we're going to do there is use the minus b formula for that, the famous minus b, plus or minus the square root of b squared minus 4ac all over 2a. So here b is minus 14, so minus b is 14. So there we have it there. And actually correctly that should be minus 14 squared. So there's b squared. For a and c, well, a is 1 and c is 1, so that's a there. That's 1, and that's 1 there as well. So it's minus 4 times 1 times 1, so that's just 4. So minus 14 squared is 196. Minus 4, you get 192. Okay, so it's 14 plus or minus the square root of 192 over 2. We can simplify that down a bit. We can make that, we can express that as 7 plus or minus the square root of 48, or equivalently 7 plus or minus the square root of 4 root 3 or 3 root 4? 4 root 3. Yeah. So let's use that. Now, so remember, this is our a solution now. W equals e to the iz, and we found that to be 7 plus 4 square root of 3. Okay, so let's get the log of both sides. Okay, so the log of e to the iz is simply I to the power iz. Okay, and we have the log of 7 plus 4 square root of 3. Okay, now we have an expression iz there. Okay, now this is where we use a little trick. What we want is z. We have iz. So how do we find z? Well, if we multiply minus 1 by all of this, we get z. So we just get z back out. So minus 1 times iz, just multiply it through. So z is minus I log of 7 plus 4 square root of 3. Okay, let's put another bracket there. Now, I just want to sort of be clear about something. This is in the form x plus iy. Okay, what we have here is a 0 that corresponds to our x plus iy. Well, necessarily, this whole thing here is the y. Now, this is just a sort of thing that people do. They might sort of think that's the x component, that's the y component. The whole thing is x and y. What we're going to do now is get the argument of that. Or sorry, we can use that expression I used at the start, down here at the bottom. Log of x plus iy. So just it's a log of the modulus plus I times the argument. Now remember, we got a negative sign here, so it's a minus y value. So we're just actually going in the opposite direction. So it's going to be, it's a 0. Oops. We got a negative number here, minus b. A is still 0, so we're just, it's minus pi over 2 this time. Okay, just a sort of, that's an answer that we should get. Anyway, I'll cut to the chase. So what we're going to do is transform that into, we have we're going to get the, how should I put it, the logarithm of that, or re-express that essentially. No, actually, scratch that. We have a good answer there. That'll do. So, yeah, that actually works. Yeah, sorry, I just get a bit too carried away sometimes. All right, so that's the answer there. 0 minus I times that. All right, that's good. Goodbye.